Good morning. It's 8 o'clock. It's actually 8:01. It's a very slow morning once again, but I don't have time to waste. Those of you that are here, congratulations, you're here because you're gonna see the full program of what we have to do to get done with Chapter 5, cover the material for the homework problems, and get you ready for the take-home exam, of which so far this week I've spent time reworking it, checking it, working the problems forwards and backwards, and just being ready for that. So homework did not get graded, but I pushed along to the point where I can sit down and grade it. I've got all the keys written out. I've got all the points assigned. I have to sit down and do it. But every time I sit down to think about doing that, I say, hey, wait a minute, something else needs to be done to make sure that you can get the new stuff done. So we'll be talking about that today. I'll also make some decisions about the project due date of next Tuesday, along with the take-home exam, and I'll let information out on that as time goes on. I may also decide to do something with the number of problems that are on set number 6. However, I haven't decided on that yet. I've done different things over the years. Just to review once again, which is kind of the normal thing I like to do towards the end of the semester. Next week is Thanksgiving week, so with that being the case, class does not meet. The fact that I've got a due date of the 22nd, and that's my wonderful going away lunch that they insisted that I have at bare minimum. That's happening on Tuesday next week. This is one of the first holidays. You know, the university takes 23, 24, and 25 off. Monday and Tuesday was taken off on Labor Day, so that makes one full week. But then when we come rolling back, then things will get more intense because we'll be finishing off November, starting December. That's week 1 after Thanksgiving break. Then week 2 is the 5th through the 9th. And then we go into finals week, and our final exam should be on the 14th, or is on the 14th. I'm guessing it's at 10 in the morning or something. I still haven't checked it again, but normally they make it at a different time for these once a week classes. So I'll check that and make sure we all know when we're meeting in here. It's an exact 2-hour meeting time, which is also normal for the final exam. The final exam will be open book and open notes. No need to talk about that right now. We have plenty of other things to do. Another thing that's going to happen, though, this week, if I can do it, or it will happen on Monday, I'm going to rework the project involving GPS. And that project is your final project. And it's all canned up. You just have to write a little bit of code, answer questions, run experiments. So you're mostly running experiments with that and learning about digital signal processing inside of a code, spreading a code tracking loop. So it's a control system application as well, and then it estimates pseudo ranges. And some of the physics modeling behind GPS is also in that document. So if you wanted to look at that after the dust settles a little bit, and I'm not thinking the dust is going to settle enough for you probably to want to look at it until after you finish the take-home exam, but it is this project right in here, DSP and GPS signal acquisition and tracking. So it's a very fun, to me it's a very fun project. I worked really hard to write the code out, and then I provided some background on it. I'll probably do a demo. There's sort of a companion project site called it's called GPS Helper. It's another GitHub project that I did with Charant, actually. And it's sort of the other side of this. This takes you so far, but this other GitHub site introduces Kalman filtering from a nice, easy book on learning Kalman filtering, and then it also takes the application example of going from pseudo ranges, which is what this project does, into actual tracking on a street map. So I take it all the way down. I take it through. I use let's see, trying to remember the name of the package in Python. It's a satellite propagation package. SGP4, I think, is the name of it. But and then I track the various GPS satellites are put into motion, and then a person is put into motion on the ground, and then he gets to map that person out. That part is not done in this project, and that's not what you have to do, but put those two together and you've got a more complete picture of things. So what did I do new on the site besides posting hints for set 6, which we'll probably be talking about? I also posted late last night Chapter 5 Jupyter Lab Notebook example, which we'll be using in class, and then there's a PDF rendering of that, just like I've done before. There are some things in this notebook that we're going to go through today that will also factor into the take-home exam, and I've hinted at these things, and I'll hint at them again when we're looking at various things in Chapter 5. So I'm now going to move over to looking at the material. Before I get started, though, I know Kaylee, you have an exam. You have a question, and maybe you just want to do it after class up in the lab. But does anybody have questions on Set 1P, the projects? I may extend them to next week, but right now they're due next week rather than after Thanksgiving. Kaylee's question is regarding problem number 3 with the polyphase filter, but you need to tackle those problems. Do you want to give any testimony about how much time you've been spending on the problems?
Yeah, I'm almost there. I just need to finish some.
So how about the Pi audio problems? Were those good?
Yeah, it was good. I had fun. I did it all in one day.
Okay, so would you say it goes faster, or would you want to rate the problems from your point of view in terms of which has been taking the most time? Yeah.
I'd say that one was just long, so it probably took me 5 hours or
For the Pi audio?
Yeah.
But once you get rolling on it, I think it goes fairly quickly.
I just wanted to do it all at once. It's not
Yeah,
really that.
okay. And you used the Julia version, I mean, you used Python through the Julia install, or just a separate Python install?
I just did the way you did it.
Okay, good. It works all different ways for me, but it's a little bit trickier. Why is it trickier, and why are we electrical engineers? Because we play with hardware. So if you have to deal with hardware and interfaces, yeah, it is a little bit more than what everybody else would have to do. If they were, say, computer science, they wouldn't worry about USB devices necessarily and bandwidth and that sort of stuff. This one's consistent, but I won't talk about it unless you've got a question. The only way things really make sense to you is if you've studied them and you have a desire to pick out the last few details. So nobody has any questions on the project. I'm going to move into 5, and we'll talk afterwards. So last week we had started into Chapter 5, and we got as far as phase distortion and group delay. I went on to do a little bit of an example, but I wanted to just roll back through and kind of review again what is group delay. And group delay, the way I like to think of it, and I don't consider myself an expert, I had to learn it just like you have to learn it, is this definition, and this is this signal model that the book uses. It says we have a signal x of n, which is represented as S of n times cosine omega naught. So if you've had COM systems 1 already, or you've had some COM systems, you recognize this as being a modulation theorem kind of example where we've got a signal S of n. Presumably it's a narrow band signal, so that means at baseband it just goes up to some cutoff frequency, say omega c. But then when we multiply it times the cosine, it shifts it from baseband, it takes it up to omega naught, right? So the idea of the group delay has to do with what is the delay associated with the band of frequencies centered on omega naught. And that's the second line here. It says we're assuming that the spectrum of x of n is approximately 0 outside a band of plus and minus omega naught. So that's kind of what this picture shows. I've got a big bandage on my thumb, which came from a cut. And this time of the year, it's starting to get dry. So I got up this morning to take a shower, and my finger's bleeding. It's like, what am I going to do? And it hurts really bad because it's a slice. Some of you probably had this exact same problem. Probably the puppy bit me. I don't know, but it turned into a big, long, gaping wound. And so now my thumb probably doesn't work on the touchscreen properly. At any rate, so this is the idea of the narrowband signal. It's centered on omega naught, and yes, it will have a negative frequency image as well, but I'm just thinking of the delay associated with that band of frequencies. So group means a group of frequencies. A group or band of frequencies are going to receive some delay. And so the model that the book talks about is finding the angle in the response of some channel or some channel that the signal is going to pass through, like a transmit filter, let's say, or band limiting filter, or a receive filter, it could be too in a receiving system. Do a Taylor series expansion of the phase response centered on omega naught, and if you just keep two terms of the Taylor series, you have a constant plus a linear term. So it's just trying to describe what is the phase. And then if you look at what is the delay that that band of frequency sees, it's going to be approximately n sub d samples. So that is the time delay received by, in comm systems, we call S of n the envelope of a signal. And if you do take comm systems next semester, Dr. Mark, what's his last name again? Dr. Mark Frank, late last night, I was in a church meeting, I saw a message come through saying he would like to teach the class, but I have to talk to him about details. So the class will be taught. I don't think there's going to be a new faculty member hired for the spring, talking to the committee members of that. But he showed interest in teaching it. So at any rate, you learn about that because you learn about basic modulation theory. And this, in comm systems 1, this would be called double sideband modulation. For those of you that have had it, and I know 2 of you have had it for sure, this would be called DSP, right? A message signal, S of n times a carrier, double sideband modulates it. So you have this sort of a scheme. So I think group delay came about from radio engineering, saying what is the delay received by a group of frequencies. Formally, the group delay, without doing the simple Taylor series two-term approximation, is got all of the components in it. So now the delay is more than just the linear delay, ND, which would be constant over the band. It's going to be changing with frequency over the band, and that's what this definition in the blue box takes into account. It gives you the full up time delay as a function of frequency across the entire spectrum. So it's minus the derivative of the argument, which is the mathematical term for the angle of a complex number, differentiated with respect to omega. And the units will be samples. So in the software that we'll be looking at that I've written in Python, I give you the option of doing a response for group delay, either in terms of samples or in terms of seconds if you want to put a sampling rate on there. And as soon as you put a sampling rate on there, then you can just say each sample delay is going to be 1 over the sampling rate in seconds, right? So then you can get the actual seconds. In a comm system, though, in the analog domain, group delay is always specified in time units of seconds, microseconds, nanoseconds, whatever. So it's this idea here that is the most interest in people talk about group delay. It's the deviation of that group delay from a constant value that indicates the degree of nonlinearity. So that's what people generally look at. And honestly, if you're looking at group delay, it jumps off the page at you really quickly. Is it a flat line in the band of interest where you're sending signals through, or has it got a wiggle to it, or is it going up or down? If you look at the phase, it will have a lot of motion in it, up and down motion. If you see straight line segments, then you would say, aha, in my mind I can take the derivative and I know if it's a constant slope, it'll differentiate to be a straight horizontal line. But group delay makes it jump off the page a lot easier. So don't think that you have to always see the group delay to see that there's phase distortion, because phase distortion you can see from the phase itself, but it's a little bit harder because you might see different portions of the response where you see different linear phase terms, but the slopes are not all the same. Then that would mean that the group delay is not constant. It would change with frequency in some way. We're going to look at some examples of that. So then I did this example, which we did go through, where I passed 2 narrowband pulse signals through a low-pass filter, and I purposefully used what we're going to learn about today, the all-pass filter, to modify the group delay in a band of frequencies centered on the first pulse, pulse number 1. And we're going to learn about all-pass filters, which show up in about 80% of the homework problems, or maybe it's 90%. Almost every homework problem in this chapter has something to do with all-pass filters. They kind of lie behind the scenes because you can do transformations with them. And the big thing about the all-pass filter is that it has constant gain, but it has phase that changes with frequency, and then hence the derivative of the phase. We're going to be looking at this application a little bit closer, but here's an example of this is one of my software tools again that I've showed you from my collection. This was written in Zojo, a cross-platform, object-oriented, basic-like language. But this is the frequency response of this 5th order all-pass, and there's the phase response of it. We'll be later looking at the idea of geometry, so I'll be moving this around and just talking about how the pole and zero placement makes the all-pass filters kind of very, very identifiable, and I'll explain more about that later, but we'll come back to this later. But the main idea I want you to know is the all-pass filter does that, constant gain, so you won't see it in the magnitude response, but the phase here is doing something, and by design of the all-pass filters, I was able to cascade a goodly number of them in here to get sort of an equal ripple response of group delay. And that's how this amazing feat of having the signal that arrives first comes out last in going through this filter. And I don't know if I showed this to you last week, and I said you might want to think about it. Has anybody thought about it and said, that's really amazing? Or I find it really amazing. It's like this is a fact of physics, but from a signal processing point of view, we can understand why. That band of frequencies gets more delay than the other band does. But in general, this filter has got a constant group delay, because we'll see this is a linear phase FIR filter, and it normally should just be this flat amount in here of delay, but it's gotten modified by the all-pass filter. But if I could have made this band here very flat with group delay, and the only signal you wanted to that you cared about was narrowband signal number 1, and if it was constant group delay in that band, you would say it's distortionless, because as long as the group delay is constant, then it's considered good. So always when you're talking about filters and distortion, you have to put it in the context of what are you processing and what is the signal of interest. A filter is always going to have amplitude distortion because it's going to pass some bands and block others. But within the context of the band of interest, does it pass through with no amplitude fluctuation in linear phase and constant group delay? So a filter wouldn't be good for anything if all it did was have a constant gain and a linear phase. I mean, that's not very exciting. What does that, by the way? Constant gain and linear phase is a transmission line, an ideal transmission line, because that would just take a signal, delay it by the propagation, velocity propagation in the medium, it arrives at the other end perfectly intact, just delayed. Just like electromagnetic waves in free space do nominally the same thing, and acoustic waves nominally the same thing, but they all suffer from, multipath. Like in this room, my voice is bouncing off of different surfaces, so you're hearing different wavefronts, right? But our ears are not really, you're not discerning that small amount of time delay. Or maybe some of you do, I don't know. You go to a concert though, and it's definitely there, right? I play my horn in a big auditorium, and the ambiance of the room or the characteristics of the room give you a nicer sound when you've got some reverberation going on. At least that's my feeling, and that's what most people say. A room that has no reflections in it is very dry and dull sounding, but it has no distortion. Okay, the next parts of this chapter whirls through a lot of different things, most of which don't show up in the homework problems, just certain sections do. So I'm going to move quickly in some areas and slow down in other areas. This section is pretty much just a review of what we've seen from chapter 2, and chapter 3. So it's just saying we have a LCCDE representation in terms of a difference equation. We can then extract from that the ratio of the numerator over the denominator polynomial in the difference equation to get the system function. And then we can do factoring of those polynomials into their roots. So CK are the zeros, DK are the poles. That gets discussed in other sections of this in a really big way, but the contributions of individual poles and zeros is one of the features of chapter 5. So this is just a simple difference equation, and then in the Z domain, the very first homework problem is exactly of this type of discussion. So it's problem 5.8, and I'm holding my solutions right here, so if you get asked questions like you first find h of z, you find the impulse response, and then it asks you find a stable but non-causal impulse response that also satisfies the LCCDE. So that would be a mixed scenario where you're going to have a right-sided and a left-sided sequence. Remember, that stuff that goes back to, we saw that in chapter 3 in the Z transform, remember, where you would say one, without knowing the region of convergence, you could generalize it and say I'm going to have one term right-sided, the other side left-sided, or the part left-sided. Another thing that's not in the book, but I took from another book, is this Schur-Kuhn stability test. Kohn, I don't know, I'm not positive how to pronounce these two guys' names, but from 3205, you would have studied the Routh array for stability of an S-domain polynomial, right? And in control systems for sure, but don't you do that in 3205 stability, or no? Okay, it used to be in there, but you do it in control systems. You were going to say something? No? So I put this in the notes because I was thinking that in the S-domain you had already seen the Routh array for finding out whether or not there are any poles in the S-plane that are in the right-hand side, because that means you're unstable in a causal system. So this stability test takes a polynomial a of z and does the same thing in the Z domain. So it's trying to figure out, do any poles lie or any roots lie outside the unit circle? In MATLAB and in Python and in Julia, they all have polynomial rooting functions, roots in particular for Python. What you're accustomed to doing is just taking roots and putting an array in there that's the list of the coefficients and having it tell you what the roots are, right? You're spoiled rotten by that fact. Dial back in time, and being able to root a polynomial was something that took more effort. You had to have a tool. So this allows you to go through an algorithm, and it also gives you the advantage of you could work symbolically if you wanted to. So this is just an algorithm. I don't ever ask any test questions on it, but this just goes through a systematic procedure, and then you can verify whether or not you have roots that lie outside the unit circle. In control systems, when you use the Rauther ray, you're studying conditions for stability usually, and if you write it in terms of variables, then you can find out, like a gain in a feedback control system, if it gets too big or if it's too small, will it go unstable? Those are the types of interesting things you can do with these theorems. And in electronics, you may have built something that went unstable. Is that part of the lab where you have the gain go big and something starts oscillating? I'm just curious. But you know it can happen, though. The thing about control systems is you'd think that only too much gain could be bad for your system. I say bad for your health, let's say, go unstable. Turns out in control systems you will find out that if the gain is not large enough, you can also be unstable. So there's some phase lock loop designs that will be unstable for either too little gain or too much gain. Okay, this topic though right here, inverse systems, which gets talked about right here in this chapter and then comes back again after we've talked about all-pass filters. There will be a problem on this on the take-home exam. So I've got some of this discussed in the notebook. So this, ideally, it says, what is an inverse of a system? It's a system HI that will undo what H of Z does. So when you take the product of H of Z times HI of Z, you should get 1. So formally that will tell you that inverse system must be 1 over H of Z. Sounds really simple. And in communications, signal processing, and in other controls applications, but for me in communication signal processing, it comes up under the topic of equalization. Can you equalize the distortion that's imparted by a channel, like a radio channel, so that you can get a better quality signal into your receiver and then have a lower bit error probability? So the inverse system is of interest. We do it adaptively with adaptive filters. We can have a fixed equalizer. One of my master's students right now works at Keysight, is working on PCIe 6, which is the latest and fastest bus standard for disk drives to talk to motherboards. And is anybody familiar with PCIe? It's been around for a long time, but now the 6th generation does a whopping 64 gigatransfers per second. It's just phenomenal what it can do. It does that with the ribbon cable and multiple lanes. But there's distortion in that because that electromagnetic structure of the ribbon cable produces some crosstalk between the lanes, and it also produces dispersion on the desired lane as it travels from the sending end to the receiving end. So he's been studying equalizers. He's been looking at a lot of different things that are also talked about in the standard. He's been interested in the topic because he works in a group at Keysight that builds test equipment and does ASIC design for test equipment, but in particular these data standards. So they're going to have a test set that will do PCIe 6, so people developing PCIe 6 devices can understand if their implementation is working to the standard and just learn more about what they're doing. So I found it interesting. It was my last student to take on. He was in my Com2 class last fall, so I've learned a lot about PCIe 6 this semester. It's one of the things that, for better or for worse, I've spent a lot of time with reading and discussing. But things are working pretty good. He used Keysight's ADS software to model his channel, the ribbon cable structure. So what is, if we have a particular frequency in the channel, or H of Z, where the response goes to 0, then we obviously can't invert at that frequency, because if we've notched out a single frequency somewhere and we try to recover the information that was contained at that frequency, it's gone forever. So, but excluding that, we can do a pretty good job of just finding the inverse system. So here, poles become zeros and zeros become poles. The region of convergence has to overlap between hi and h of z. So in particular, if h of z is causal, then we can go ahead and go after the inverse. But one of the problems that we're going to run into is the poles will be inside the unit circle if it's causal, but the zeros don't have to be. So since the zeros become poles, if we invert the system, the zeros will become, the poles will be outside the unit circle if the zeros were already outside the unit circle. So that's one of the limitations of just directly forming the inverse, is we'll form a non-causal inverse because we'll have some poles outside the unit circle, and of course the poles that were inside the unit circle will become zeros inside the unit circle. We'll motivate that further when we get into the all-pass filter, but now I'm going to spin off of this example right here, which I did in Jupyter, and added it to the Jupyter notebook in here. So it's this topic right here, equalization. So this is exactly the problem that I have in the notes. You notice there's a 0 at 0.5 and there's a pole at 0.9. So if I form the inverse, I'm good to go, and I can perfectly recover this, because if I flip this thing over, both the pole and the 0 are still inside the unit circle. So here I just formed some polynomials to correspond to polynomial coefficients to correspond to the numerator and denominator. So I'm looking at my letters here, and it looks like I may have actually done something, labeled something backwards. I've just got to look at this. B. I've got them flipped around though, so I think I'm probably still okay either way I do it, but I think this should say, I always have to do something messed up. I messed around with this all day yesterday. Okay, B1, that's this guy right here. A1, that's this guy. Now the inverse system is going to have B2 have the 0.9, and A2 is the denominator. If I take the product of HI and H of Z and HI, I get back just 1 over 1. So let's just run that. So down here I'm using a function that I have in my IIR design helper and also FIR design helper, an easy little routine for overlaying plots. Those of you in the lab have already seen this demoed a bunch of times, but here I'm just taking 3 different designs, and I'm going to use this frequency response list to take B1 over A1, B2 over A2, and B3 over A3 and do the plot in dB. And I can do it phase, and I can do group delay. So here's the original system is a kind of a low-pass response. The inverse system is coming up, and notice what it's doing here in dB at least. The gains are canceling each other out in dB, so we get 0 dB gain. And that's the idea of the inverse function. It's going to try to flatten the response, because the amplitude response has been shaped somehow or another, and that's what we want to remove with the equalizer or the inverse system. So that is the first ground rule. The equalizer or the inverse system is to try to undo what the channel H of Z does. So there's what it does in amplitude. I will comment that line, go down to the next line, uncomment it, and run it again. And there's the phase response. Same idea. I mean, it's doing the same equalization for both amplitude and phase. If I now go to group delay, I don't have B3 and A3 listed in the list here because it's hard to take the derivative of a constant over a constant and get something, because what are you going to get? You're going to get something that's going to go unstable. It doesn't make any sense. You can just look at a transfer function of 1 and say the frequency response is flat, the phase is 0, and the group delay is 0. It's hard to numerically not get upset about doing that, though, so I just simply took it out. But what you can see, I have to take this factor out. I think I'm going to have to make this go, well, let's do it. Yeah. So there's what the group delay is doing between the two systems. They both have, one has positive group delay, the other one has negative group delay, and they taper down towards 0 group delay as you get further away. But when you cascade two systems, the group delays add, so this nominally is how we got the 0 group delay in the beginning for the cascade of the two systems. This also, since I'm showing this picture right in here, you might be wondering, hopefully you are wondering, what does it mean if a system has a negative group delay? Because if the units are seconds or samples, that would mean that we've created a filter that can predict, right? If it has a negative delay. Okay, so I've spun my wheels around on that and done analysis on that. And if you drive into that, you find out that from the definition of group delay, you can have a negative value, but if you actually look at the physics involved and look at, does the signal actually come out earlier than what it goes in at, it doesn't happen. It doesn't work that way. The mathematics kind of break down, actually. It's sort of like a paradox type problem. I don't want to get sidetracked on it, but I'm bringing it up because I don't want you to think that we could build a magic filter that would put advanced time like that, where we could predict the future. It doesn't work that way. But the math lets this behavior kind of show through. So now, what about a system with a non-causal inverse? So this is one of the problems on exam 2. So make note of this. You'll want to come back and revisit this probably. This is like a giant hint. There are hints in the take-home exam itself, but this is an even bigger and bolder one that's in there for the particular problem. I'm not going to explain the details of the problem, but I am just going to take it through an example. So here, and this will get talked about a little bit later today, here I've taken a system that has a 0 at 2, and it still has the pole at 0.9. So when we learn about all-pass filters, we're going to learn about how we can do some transformation on this so that we can end up creating what's called a minimum phase system. And right now, this is not a minimum phase system, but we will be learning about that shortly. The idea of the minimum phase system, though, is where both the poles and the zeros lie inside the unit circle. That's called minimum phase. And right now, one is outside and the other one's inside. So the technique that we'll more formally discuss and can be implemented with an all-pass filter added into this system is to reflect the 0 that's at 2 to inside the unit circle. And reflecting means I take 1 over the conjugate, or the conjugate reciprocal of 2. So 1 over 2 conjugate is 1 over 2, and that's 0.5. So that means I'm going to flip it inside. And here I have the same screwed up thing that I was doing. I don't know how I did this. That was supposed to be B, that was supposed to be A, B, A. That's still good. So here, I've got h of z with a 0 at 2, and a pole at, I don't know why I have the minus sign. Oh, it has to be in there. Never mind. That has to be in there because it has to follow the coefficients here. And then what I'm doing with the inverse system, I'm going to put this minus 0.9 in there for the 0, but then rather than putting in the pole, having a pole at 2, because that would make the system non-causal to still be stable, I'm going to invert it. I'm going to reflect it. So I'm reflect the 0 at z is equal to 2 to z is equal to 1/2. And does it work? I'm running this as a causal system, so yes, it does work. You can see that the gain comes out flat. It is not 0 dB anymore, and we're going to explore why that is. It has to do with the introduction of the all-pass filter. I'll be reposting this, so I'll fix my typo there. It doesn't bring it back to unity unless we introduce a scale factor, and I'm going to go through that today. And the phase is no longer linear either, so let's just see how that got messed up here. We'll look at the phase response. And the composite is green, so it's no longer 0 anymore. That's because we've done a causal representation of the inverse rather than the non-causal representation. And why do we care about that? We want to implement it in real time so you can't tolerate the idea of having a non-causal system. But we have flattened the gain. What does the group delay do? The original system has a group delay which peaks. Because I inverted things, this should be, I need to change these around. I need to go -8 to 11 for my range. So the original system had a group delay up at 11, and then it settled on down. The inverse system, the causal inverse, had a group delay that peaks at -8. When you cascade those together, you do get an improvement in the overall group delay, but it's still not flat. But it does range over smaller values, which means it introduces less delay distortion. The exam problem will make this really clear. It's actually it's a really nice little problem based on digital communications and characterization, which you're going to learn about in the problem, but this does effectively work. It's how to deal with a multipath channel, and how does this come about in a practical radio communication setting. It can happen when, if I'm standing here and I'm looking at the cell towers up there, if I don't have a direct path to me that's as strong as, say, a path reflecting off the building right behind me, that will mean a path that you have to travel further is stronger than the direct path. So that creates this situation. If I remove this denominator right here and just looked at the numerator, that would say the direct signal had a gain of 1 and the indirect signal had a gain of -2 or 2, whatever. So that means the signal that came to me later was stronger than the signal that came to me directly. That's how you get a channel that's non-minimum phase, is the terminology a communications person would use. And that's what this exam problem will illustrate. I hope it works well for you. I mean, I've laid it all out. It's I realize when the first time you see something, it might not settle really well, but hopefully when you do what I've asked you to do, and there's code that leads you along the way in that, so I think it should be pretty good. We'll come back and talk a little bit more about this. In particular, we'll talk about how we could make the inverse system, which is non-causal become causal by the use of an all-pass filter. That's the big deal. It's not just simply inverting, taking 1 over h of z, because when you do that, you have a non-causal system. It's then also applying an all-pass filter to make it causal. And that's the idea of flipping the 0 that's outside the unit circle to the inside. And the all-pass filter is going to do that. Any questions on this? Is it interesting, or just like, I can't get too excited about this? I mean, face it, we're beyond the basics, so now we have to make things more interesting by kind of diving in deeper and just sort of exploring some of these things that are going on. Okay, the next topic the book has is impulse response, just being able to use partial fraction expansion and doing long division if it's not proper rational. Kind of seen that before. Okay, next section, frequency response for rational system functions, is kind of drilling on the idea that we have poles and zeros if we root the numerator and denominator polynomials. And if you want to study the 3 different performance measures of an LTI system in terms of poles and zeros, we can go after the magnitude response, which is right here. So we have terms in the numerator which are the magnitude of a vector times the magnitude of another vector, and so on, because we have a product of these terms, and same in the denominator. So we get contributions from all of the zeros and poles. Phase response, the same way. We have angles associated with each of the poles and zeros, so we add and subtract the contributions from the zeros, subtract the contributions from the poles, and then there's a contribution from B0 and A0 only if there's a sign hanging out in there. If that happens to be -1, then that would be 180 degrees of phase shift. That also forces the discussion of what is the principal value of the phase. That's what we get when we use phase in MATLAB, Python, and Julia, but it's always the principal value, which lies between minus and plus pi. Sometimes we like to be able to unwrap the phase because the principal value doesn't show us everything that we really care to see. We don't recognize the fact that the phase may have gone around, may be a result of going around the circle more than once. So there's a function called unwrap, and little arg is a continuous function of phase that unwraps the phase. So just a case in point is if I take this linear phase FIR filter and unwrap the phase, I will see something like this, where we can see that there's a constant slope, and this is what I was talking about earlier with group delay. If we differentiate this, we see that we're good in terms of having a constant because the slope here is the same all the way along. We just have these jumps by pi, and the jumps by pi can occur when you have a 0 on the unit circle. I'll explain that shortly as well. That's what you'd get if you just use phase directly. So you see the wrapped phase, and you can't quite picture what's going on. The unwrapping takes it through and notices the jumps where we have a 2 pi jump. We unwrap it to keep it going downhill like that. I didn't put an example of that in the notebook, but there is a function in MATLAB called unwrap. There's a function in Python called unwrap, and I haven't really explored whether Julia has unwrap, but I would say that it probably does because the other 2 languages do. It's just a function that will unwrap the phase. Now, kind of a favorite topic of mine is geometric evaluation. Can we get an idea of the response shape and magnitude and phase just from the pole 0 geometry? So this continues from earlier part of this section with responses by homing in on the idea of using geometry. So here the idea is to go back to the Z domain, so that way in the complex plane we can think of each of these numerator and denominator terms as being a two-dimensional vector, because Z is somewhere in the Z plane, so it's, in particular we want to consider it just on the unit circle, and then CK is wherever the pole is, or zero is located, DK is the zero, so we're forming a two-dimensional vector if you think about the complex plane as being real and imaginary parts being two-dimensional vector space. So each of those vectors in the numerator has got a magnitude and a phase. Each of the vectors in the denominator has a magnitude and a phase. And from those we can, say, get the magnitude response by taking the product of all the numerator vector magnitudes divided by the product of all the denominator vector magnitudes, and then include B0 over A0 if necessary for a particular system. Similarly, you can find the angles that each of the vectors make to the positive real axes, and then we're going to be adding all the angles from the numerator and subtracting all the angles from the denominator, and then depending upon m and n relative, we get some linear phase out of this term right here. If we look at it as e to the j n minus m, that's just a linear phase contribution in the overall phase response. So a simple example would be just a single zero in a system, and then just looking at it. What is the geometry of this system? We have a zero, and then we end up with a pole at 0. So this last line here is just showing there's two vectors. There's a single vector for the numerator and a single vector for the denominator. And if you draw a picture out of this, that's the 0, that's the pole. So if you put yourself somewhere on the unit circle in the z plane, the vectors are v3, which I've got denoted in here. And then we have vector v1. And then we're considering, for the magnitude, it's just the length of the v3 divided by the length of the v1 for any value of omega, is what we're doing right there. And that is in this expression right here. It's implicit that it's a function of omega. Let's just take a really simple example. This has got just zeros in its response, but it's got 5 zeros rather than a single zero. And these zeros all are located on the unit circle. So when I'm at a particular value of omega, I'm at some place on the unit circle, and I have all these vectors going from the zeros to the blue dot. The lengths of those vectors are multiplied together, and then you divide by the by the denominator vector, which is a bunch of poles all stacked up, because there's going to be 5 poles here at z is equal to 0, right? That's the balance that we have to do in positive powers of z. But the lengths of those vectors is all 1, so it doesn't change. But as we're moving along in frequency, here we get the largest amplitude response, And then as we get close to the very first zero, we have the product of these vectors in here. Oh, this, yeah, I screwed up. This is 5 taps, but the order of the polynomial is 4th degree, so there's 4 zeros. This length is short. This one is still pretty long. The other two are very long, but this one is short, so it's driving the overall product down towards 0. And of course, when I get almost right on top of that 0, nothing gets through, right? Because I have a very short vector there in the product of all those vectors. And then it bounces back up again and hit that one. The same thing happens. This now shows you the symmetry of a system with a real impulse response, because as I go on to the negative frequency values, I just traverse everything, but I'm coming back, and now I'm back to the beginning again. That's just a dB plot, which for this one, it's a little bit more, it's not quite as nice, but in the dB plot, these holes are down at -infinity. So what I'm trying to do is connect your brain with the idea of pole and zero placement. In this case, just zeros, because the poles are all at z is equal to 0, which means they don't contribute any magnitude response. They do contribute linear phase. But from the geometry, you can sketch out kind of what's going on. And I'm going to do a little example of that in Jupyter next. Is this interesting? I mean, this software is available if you'd like to play with it. Actually, I forgot about this part of it. Here are where the roots are of the zeros. Or in polar form, you can see that for this particular set of coefficients, all of the poles lie at a radius of 1, and then their angles are, as you see in the picture here. So we looked at the all-pass already, and we'll come back to it. And I'll probably look at this again, so I'm not going to spend any time on it right now. But how about an elliptic filter? I'm going to put this one in dB. So for the elliptic filter, when you design the elliptic filter, you end up, for elliptic low-pass filter, you end up getting a bunch of poles sitting out there, sort of on the right half side of the, near the edge of the unit circle, and they're describing the ripple that we're seeing in here. When I'm zooming around here, I'm hitting close to a pole, but I'm close to some zeros, so I'm not shooting up to infinity. That pole is not on the unit circle. It's close, but not that close. They're positioned in such a way to get equal ripple in here. I can kind of magnify that a little bit, but I don't have a lot of flexibility in the way I wrote this software. I wrote this software over probably about 20 years ago, actually. I wrote it from scratch, all the graphics and all the stuff to grab stuff. Has anybody ever done anything like coding where you have to work with graphics and mouse control and finding points? I mean, it can be done. It's just, I set myself in. I'm a very determined person, though, in case you haven't noticed. I strive for things and try to get there if possible. So those poles are situated such that it defines the pass band. Then we go through the transition band, and now we're hitting the zeros along in there. So just for the fun of it, move this to the bandpass domain. And there's a bandpass filter, so everything just rotates around. The poles are now sitting at this, sort of straddling the center frequency, which is at 90 degrees, or pi over 2 radians. And the zeros sit either side of that, again on the unit circle. And if we move this around, you can see how we're hitting the zeros, and then we hit the pass band and have the ripple in the pass band and come down. But it's the product of all of the red lines, the lengths of those red lines, divided by the product of all of the green lines, which are in the denominator, that form the magnitude response. The angles each of those vectors make to the positive real axis are added and subtracted to get the phase response down here. Make sense from what I'm describing? There's really no homework problems on this. There's no exam problem on this, but there could be one on the final. I haven't decided that yet. Interesting. I mean, this sort of opens your eyes up into how you can visualize from a pole zero plot a little bit about what's going on. You can't get the fine detail unless you actually sweep it in frequency. So I'm going to move this back to the all pass for a little bit later. And now what I'm going to do is jump back into Jupyter. I'm going to skip over these IIR examples. I guess I should run them to see if they run out. These are kind of going back to group delay, but this is the notch filter that you're playing with in Project 1. This is the FIR notch, which does not have the denominator, and the IIR notch, which has the denominator, which puts some complex complex conjugate poles just behind the location of the zeros on the unit circle to sharpen up the response. And you can see that with the FIR, the phase is linear. IIR, the phase is very sculpted and shaped. The group delay of the FIR is flat. It's a one sample delay because it's a second order system. So just from the math here, I can see that this is going to have a one sample delay because it's got 3 total taps, so the mean delay is going to be one sample halfway through the filter. The IIR version has a very non-constant group delay. As a matter of fact, the closer I put the pole in there to the unit circle, like if I go to 0.99 in this model, very nice notching effect, very pinpointy thumbtack. If you look at that, I look at that thinking that looks like the profile of a thumbtack, right? Thumbtack in the paper and then the needles coming down. That's sort of the shape of the frequency response. The group delay, though, right at that frequency that's getting notched is 100 samples. It's like, but does that bother me? It doesn't really bother me because I'm not passing a signal. The gain there is 0. So that group delay is not destroying me. The group delay is nice and flat out in the signals that I want to pass. So I could say go figure, but I'm not saying that in a sort of a crass way. I'm just saying think about it. Sometimes something you get excited about won't even matter. There's a lot of things in our physical life where it looks like that's going to fail, and you think about it, I'm probably okay because it's not going to fall on me or something like that. I don't know if that makes perfectly good sense, but so the group delay does peak at that point. So now, what's something that I'd like you to be able to do or visualize if I was to give you a problem here where I'm just giving you a configuration. So here it's a configuration of a 0 at minus 0.9, and then I've put up a pole at, or another 0, I mean, at 1.2J, that's this guy here, and then another one. Oh, this is, 1.2J, that's this one up here, just factoring it together, and then another one here. So can I get the frequency response? I can't get it at all values around the unit circle, but if I go out here along the real axes, I can use geometry to get it because I can just consider what are the vector lengths that the zeros are making to a point. So if I'm looking at 0 frequency, I have in the numerator a vector of length, what? What is the length along here over to this 0? It's 1.9, right? And what is the length that these other zeros up here are making? I can just use geometry to get that. I can use Pythagorean's theorem, right? I can take the square root of the sum of the squares of the vector length. So here I've got the vertical part is 1.2, horizontal part is 1. and then the same thing here over to there. So rather than writing out all the details, I used a function in NumPy's linear algebra subpackage called norm, which computes the does Pythagorean's theorem. Just to prove it, this is a standard from physics. If you had a vector at coordinates 3 and 4, what's the hypotenuse of that? Do you remember seeing this in physics all the time? I did. Remember the 3, 4, 5 triangle? Does anybody, do you remember that? Why did they do that? For people like me that are old, we didn't have calculators in the beginning, so they always set up problems with standard values. You're going to have to use a calculator. So I just plugged that in, and yeah, sure enough, I get 5. So that'd be the square root of 9 plus 16, right? So I just used that down here to take these vectors. So here it's on the real axis, so I just took 1 minus a minus 0.9, and then times the length of the point up on top on the imaginary axis, or I mean up on top, sitting right up here at 1.2 j, and did norm on that, and then times the one that sits down below, and so I get 0.463, and then I can work around if I want to get the response right here at pi over 2, I can draw a vectors from these 3 points to there, and again use right triangles to figure out the product of the hypotenuses of the 3 triangles. There's 2 that lie on the imaginary axis, so those are easy, and then this one, and then finally come over to here. So I did all those cases in here, got 3 values, and then just to check my work, I went into freq z, and I have to put in the polynomial b1 and a1. a1 is just 1. I define that way up here because there's just 3 poles at 0. But then I just said, let me evaluate it at 3 frequencies, 2 pi times 0, 2 pi times 0.25, which would be pi over 2, and 2 pi times 0.5, which would be pi. And then I'd be looking at the magnitude of that, because I was interested in magnitude response only at this point. And there's the 3 values that I get down below. So if you were doing this on an exam problem, you would just plug it in. You wouldn't be using freq z on the exam, but you could use your calculator and do the same sort of thing. I put it in here just to cover my bases for the future, not for what's coming up right now. So if you do play around with this, we get the magnitude response pretty easily. To get the phase response, it's a little bit trickier because what's going on here, I want to try to emphasize this if possible. I'm finding out my Band-Aid does work with my touch screen. I can touch it and it works. But when we're right up here with getting an angle, in other words, when this blue point moves up, say, right to here, and now I've got this kind of a scenario, I can get the angle depending upon the location. What I've got drawn originally is the angle for the position shown, but I'm interested in the angle relative to the positive real axis. So what happens when omega on the unit circle there gets close to the 0, it moves past it and it quickly jumps around an angle. It goes from being an angle close to 2 pi, this angle right here is, and then when it just passes by it, the angle initially is 0, so it jumps by 2 pi when it gets close to something. Or if the 0 is right on the unit circle, it just instantaneously bumps like that because it's coming up, and all of a sudden now the angle was about 2 pi, and then the angle is instantly 0 or close to 0, and then it starts increasing again. It's just a geometry kind of effect. I'm also fond of drawing pictures in 3D. I did these in Mathematica years ago. This is the rubbery surface idea that I was telling you about back in chapter 3, where I've got a pole at z is equal to 0, and then I have a 0 down here at, what was the example? A 0 at 0.8. So it's on the real axis at 0.8, and the real axis down in here. And the unit circle, if I visualize that as coming down and cutting into this surface, if I cut the surface right on the unit circle and then get that value of the 3D map out as a linear, roll it out then on a sheet of paper, that's the frequency response magnitude. So we're going to get close to 0 when we get close to this 0 in the magnitude response. The fact that there's a pole sitting right there at z is equal to 0 doesn't really threaten us. It is a pole going up to infinity, because that's what poles do, but it doesn't really threaten us because we're traversing around on the unit circle. We're never going to go in. So does that picture make sense? The idea of the rubbery surface and there's a pole and 0. I take a bunch of different examples in here and I move the frequency around. So there's the magnitude response, there's the phase, and there's the group delay going on with this single 0. And there's that freaky negative group delay for this 0 that looks like it's non-causal that I was talking about earlier. Here's sort of a drill down on what happens if a 0 is on the unit circle and how it jumps instantaneously when it hits this point. This is showing you as it's getting close, and then as it's moving away, how the angle jumps. And you can see that in here. This is the jump that occurs right when it goes through that 0, and it gives that big group delay spike. And we were seeing that in that plot in the notebook moments ago. I took a bunch of different cases, and I just don't have time to go through all of them. This is conjugate poles. And what this shows you, though, from the map is that this is how you can build a bandpass filter. You've got, in this case, 0's at 0, and then you have 2 poles just inside the unit circle, but you're cutting down into this 3D surface on the unit circle. So if you go through all the math, or you just plot it in Python or Julia, whatever, you get a peak at that location, which is due to the pole, and then it repeats again because it comes around the backside. I did a moving average filter with 8 taps, so it's a 7th order filter, and this one, I like this one because it represents trees in my backyard. There's many poles sitting in here at z is equal to 0, so it looks like the trunk of a tree because it's being pushed up to infinity with not just one term but many terms. So it's like it's super thrusting, which is why it's rising so rapidly. And then the poles that are around on the unit circle, or 0's that are on the unit circle, like in this picture, to me look like I said, what I've had in my yard is rodents that like to make little holes into the ground. So those are the gopher holes or whatever, voles, whatever you call them here in Colorado. And we saw this a long time ago in chapter 2, where we build the moving average filter. It has the 0's on the unit circle, gives us the nulls, the phase jumps, and so on. Here's a bandpass resonator. It's an improved bandpass filter because what it's going to do is it's going to place 0's due to this numerator right at pi and 0. So this is an improved resonator because the poles are sitting in here, and you get a peak when you get close to that pole as you travel around on the unit circle. And having 0's at 0 and pi makes sure that at the extremes in frequency, you pull down exactly to 0. You just don't drop down in so many dB. You're right at minus infinity dB in the response. And there's a picture of that, and this is a linear plot though, but it's tying down to 0 at each point. And when you see that in this response, you say, yep, there's got to be zeros there that make that happen. And then passing close to the poles gives you the peak. If you move the poles closer to the unit circle, you'll be on the part of this 3D surface that's risen up even higher, so you get a sharper response. That makes sense? It also makes you clearly see why you can't put the poles on the unit circle, because then it would be unstable, because you'd be going up to infinity. Let me see what I put in the notebook. I don't think I did anything more on that in the notebook. But I do have another function. In my collection of functions, I do have this guy. This one's even more fun to play with because you can, in MATLAB you used to have something like this too, but you can put poles and zeros around. So what we've just been looking at, let's see, can't do that. I can't put a single 0 down because that makes a complex system, so I have to put conjugate 0. So this is conjugate 0, but you can see in the magnitude response how we're going to get, a dip when we put the 0 right on the unit circle, or maybe a better one would be to go do this. We were just talking about the bandpass resonator, so we can put it close to the unit circle to get the magnitude response we want in dB. And then we were talking about putting a 0 there. And then this guy we don't need anymore, so I'll remove that one. This was the resonator we were looking at before. Does this help you more with geometry? I mean, we don't design filters by this unless it's a seat of the pants quickie thing where you just want to get an idea of what you can do. We use filter design techniques like Butterworth, Chebyshev, and so on, but you can also visualize things just in terms of geometry. And by virtue of the fact that I wrote both of these programs, you can see that I became fascinated with this. So maybe I'm not crazy, but sometimes I feel like, I'm just really interested in understanding it more. So I created this. Does anybody have something they want to see? Check out something that you're curious about right now that you can see what you can do, add and remove. You can also put polynomials in, and once again, I also have the locations that are being displayed in here too. Challenge the system for something.
Is it possible to have a pole at infinity?
Yes, but in the way I wrote this software, they will occur naturally just because of a lack of something, right? If we have a pole at infinity, that would mean that we have a 0 somewhere. So it's not going to, in the z-plane it will go off to infinity, but on the unit circle it will not. So I think I can try to represent that. Not positive though. I wrote the software in such a way that if I remove all the extraneous poles and zeros, I'm going to always have something to keep it in equilibrium. So here, but this will help though. There's a 0. I can put the 0 anywhere I want, but what happens if I start moving this further away? And I think I'm using my mouse scroller now. As that pole gets further and further out, it has less of an impact because it's causing a rise in the rubbery surface that I've been describing, but it's having more negligible effects along the unit circle. But we know if we have a pole out here, our system is not causal. We know that. I guess I could do the same thing. I can put it up there, just put it wherever I want to. Have they ever done this before? Not exactly, but. And by the way, this frequency response analysis is based solely on the geometry. So the system can be causal, it can be anti-causal, it can be left and right-sided. So I can do things that you would not normally think of doing. Let's just show you what I mean. No one's actually has asked any questions when I've demoed this for quite some time, but let's go back to this resonator. This guy right here. Based on what I've already told you about reciprocals, we in that equalizer we were able to get a magnitude response that we were desiring, even though the phase was not perfectly canceling. So based on that, if I put these two poles right there, or if I put them at the conjugate reciprocal locations, which is right out there, it does not matter because of the geometry says I can do that. But if I want to implement this in real time, I can't implement that because it's not going to be causal. But it does make sense mathematically. I can do that. It doesn't really care where I do it. But I can't build that. I have to have it inside like that. But I can put the zeros anywhere I want to. I'm not constrained by where they're at for a causal system. They're obviously messing around with my gain. I think part of being an engineer, though, is tinkering. So that's the reason why I created this, because I wanted to tinker with it. Did I create it without having seen anything else? No, MATLAB had something early, and then it disappeared, and then they might have brought it back again. And I've seen other textbooks have some discussions, but I wanted to make my own, so I made my own. What was the hardest? Two hard things about this were the graphics part is part of it, but to root polynomials, I bought a library for the language, so I bought IP so I could root polynomials without having to write my own. I first tried to write my own, and that was another exercise. How do I root polynomials? Think about that. If you had to write your own routine, it can be done. You just start cruising around. I learned about it from a book called Numerical Recipes, which is in the library. There was numerical recipes in C, numerical recipes in Pascal, in BASIC, a bunch of different languages. Those books, I learned a lot from those books because they took you inside of algorithms. Whereas now, with MATLAB, Python, Julia, we don't think, you don't have to think about how to write your own code, but when you get involved with being in a language where you don't have support like that, then you're forced to go look at getting something portable for your needs. And that still happens to me today when I'm having to write stuff in C++. I don't necessarily have the IP. I don't want to buy the intellectual property, so I want to figure out if somebody posted an open source solution. That's the more common thing today that we do. I'm going to come back and use this one later. So hopefully you're appreciating the fact that chapters 2 and 3, and then to some extent also in the chapter 5 with multi-rate that we learned in chapter 4, come into play. So you didn't get to this point of understanding without having the basics that you've seen earlier in the semester. And if you don't believe me, just think about it a little bit. You have to have foundations, so layer upon layer gets built, and You know, for me, I'm in year 39, so I didn't start out with DSP until I got my doctorate, so I don't have, but I have at least 39 years here, though, of doing it. So more years makes a difference. So the next big topic, there's really two big topics that remain. Relationship between magnitude and phase, which will of necessity bring into play the all-pass filter. And then the final topic will be linear phase filters and what's called generalized linear phase. So there's really just two topics that remain in this chapter, but there's facets that come into play. So this is a really interesting thing, relationship between magnitude and phase. And the book, I like what the book has to say about this. If the magnitude response is known and the number of poles and zeros is known, then there's a finite number of choices for the phase. And you have to think about that a little bit, saying magnitude response is known, but, and I know, and the number of poles and zeros known, I can get different phase responses all with the same magnitude response is what it's saying. If the phase response is known and the number of poles and zeros is known, then to within a scale factor, a finite number of choices exist for the magnitude response. So it's kind of like in advertising, they show you the product, but you don't know what's inside. You don't maybe know until you buy the product, like how did they do something? And you might, after you buy something, it's like you'll say, oh, that was silly. Why did I spend so much money for that? I could have done that myself. So that's just something that popped into my head. So the analogy of that to this is you see a frequency response, but you don't really know about the phase, and you don't know if the phase response is going to be what you want. You could have a finite number of choices for the phase and still maintain the same magnitude response. And it just gives you some idea. Your brain can go off and wander. So the way you get into this is you start with looking at the magnitude squared of the frequency response, and then write that as h times h conjugate, but then use the theorem that we had in chapter 3 for the z domain, where we're going to have h of z times h conjugate of 1 over z conjugate, because there's a theorem that talks about this, and then you set z equal e to the j omega. So it's this form that allows us to write this function c of z, which is the z transform representation of h of z times h conjugate of 1 over z conjugate, and that's then by substitution of z equals e to the j omega becomes the magnitude squared response. So when you put this together, this is what we have for the factorings in terms of poles and zeros. So the ck and dk, zeros and poles of the original system, and then this is what we have with h conjugate of 1 over z conjugate. And that the two conjugates is just necessary in order to get what we're after in the frequency domain, namely h conjugate of e to the j omega. You have to put a second conjugate in there, and that makes each of these be conjugate or be conjugates. And then because there's a z in here, these zeros and poles are actually at their conjugate reciprocal locations. So if one pole or zero is on the inside of the unit circle, then the other in those pairs there are on the outside. If one pole or zero is on the unit circle, then the conjugate reciprocal is also sitting on the unit circle. So in this picture, I have a 3-pole system and a 3-zero system. So when we look at C of Z, we see sort of a sea of poles and zeros. For every single pole like this guy right here. There's its conjugate reciprocal for that pole, and so on. So there's, if you think you're seeing double, you are seeing double, because we're seeing 2 of everything because of the way this factoring is to get C of Z. But what it tells us is, for the first part of the assumption is, the magnitude response can be created by selecting 3 poles and 3 zeros, whichever you like. You can mix and match them. So what I've got written down here is case 1. We can pick all the zeros inside the unit circle. We will always pick all the poles inside the unit circle to build a causal system. So kind of according to those properties, we'll start by saying we're going to assume those have been chosen because we want to be able to build a causal system. So that's part of our H of Z. And then for the zeros that are left over, we can either pick the ones, combinations of either being inside or outside pairwise. So if we choose those zeros to be also inside the unit circle, that's what's defined as minimum phase. It's formally defined in the notes in the book a little bit later, but that's case 1. And then we can go through all the different cases and combinations, and maximum phase would be, we can't change the position of the poles because that will make it non-causal, but we could take and choose the 3 blue locations for the zeros, and then that will be what's called maximal phase. And the details of maximum and minimum phase come out in a bunch of properties in the notes here and in the chapter. Different properties a system has, whether it's minimum or maximum phase or a mixture of the 2. If this seems a little bit abstract, it is, but it's just kind of giving you a perspective that you've never had to think about before. And sometimes you do this on purpose. Other times it's what comes at you because, say, in the radio channel I was talking about, you might get, your radio channel might have Z6 when you'd like it to be Z3. But the physics of the channel is, that's the way it is. You can't go in and change it. But if you want to build an equalizer, like we were talking about in that example, we can move the 0 from Z6 to Z3 with an all-pass filter, and that will be inherently a part of our equalizer then. It'll change the phase response, but the magnitude response will be preserved as a result of this selecting operation. I think I'm going to favor taking the break right now so you can get your brain reset a little bit rather than going deeper onto this. It's very interesting though, and I'm going to make sure I keep my microphone cable plugged in. You guys don't know what narration was all about, but it was a pain, a real pain to make it, but I cobbled something together. So I'm going to suspend right now. I'll come back at about 9:50. Well, I'm going to resume the recording even though it's not quite, it's a little bit early, but everybody's back here. While you were out, we were just talking about COM2, or COM1, I mean, who there's an instructor at Emergent who I'm going to be talking with. I finally get to talk to somebody to hand something over to you. It's like, I thought when I started, that's the way my career would end, and it's just exceedingly disappointing to not be able to hand stuff over. I gave a lot of stuff to Dr. Semiari. He started teaching off notes, and everybody that was here before he was here, the 2 other faculty members, I thought, this person's going to be the next person doing what I'm doing. Then they left, then they left, then they left. It's like, this is disgusting, disappointing. But the times are hard still. So if I can hand over something to somebody, that would be great. I think I'll probably be able to keep my website up for a while. I'm going to argue to IT at least that it's a resource to help transition new faculty in. And if the IT say that as an emeritus faculty I can't have it, I think they have to make an exception. I'm on the college's web server, so. Okay, back to what we were talking about before the break. So the big thing we've just learned is that we can look at any system and we can look at it as minimum phase, maximum phase, and anything in between. And when you're doing this dancing around, if you want to build a causal system, which is the way our mindset is always going to be, you will first say the poles have to be the poles that are inside the unit circle, and presumably that's where they're starting from. But the zeros that might be outside the unit circle could be moved inside if you wanted to make it minimum phase. So you've got all these different variations, and along the way, how do we move things around, and can we even do more than what we've done? We can incorporate a factor. If we start off with a system that has a zero outside the unit circle, we can move it inside, and vice versa. And that factor is this guy right here. So it's known as a first order all-pass filter. And what it's going to do then is, if you just look at it in this first form, it assumes that you've got a pole or a zero that you want to move, and then the numerator and denominator of this are conjugate reciprocals. So if we refactor it, which is what I do off here to the right, this numerator, you don't see that as the zero unless you refactor it to write it as 1 minus something, z to the minus 1, then you know that that is the zero. The zero is at 1 over a conjugate. And then something that the all-pass filter has that goes along with it is you end up factoring out this minus a conjugate. So there's a DC gain, or there's a gain factor that goes with it that I wasn't incorporating into that example earlier. Remember, the gain shifted when I did that causal inverse. It shifted up. It was still flat, but it wasn't 0 dB. And that's because I didn't incorporate that factor into that model. So we can use all-pass factors because they have unity gain, and this representation down here with the factoring just shows you that the gain is indeed unity. There's kind of like there's a nth order all-pass system over here. A proof of it is right here. This is what the nth order all-pass looks like. They all have the same property of unity gain, or at least a constant frequency response, but the way it's defined here, it's unity gain. And the way you can see that and prove it is to consider the polynomial as being the denominator d of z, and then d conjugate of z to the minus 1 is what you put up in the numerator. And if you study then what the magnitude of that is, you have this z to the minus n that factors out. That magnitude is 1. And then look at what's going on here. Since d conjugate of e to the minus j omega, the whole thing conjugated, is the same as d, because you've now double conjugated everything. The conjugate moves in here, flips the sign there, and takes that conjugate away. What's this magnitude has in it is identical in magnitude form, so it's 1. So it just shows you that it has got unit gain, or constant gain, but unit gain according to the definition for all frequencies. And the curious thing about how this works out when you refactor it, the polynomial coefficients go in the opposite order when you go from the numerator to the denominator. And I think I wrote that in here. I'm trying to remember, where did I put it in? I didn't do it there. So I'm going to show you in a Jupyter Notebook where I did that. So here's the first order all-pass. Here's the higher order all-pass design. And here I've written it in negative powers of z. But what you can see is that we go 1, A1, A2, A3, up to A to n. And what we have up here in the numerator, we've got the leading coefficient is the conjugate of A to the n, and then A to the n minus 1 conjugate. And then the highest order term has just got 1. And so what that means is we can build an all-pass system by just flipping the polynomial orders around. Here I've got in the numerator with minus 1/2, 1. Flip that, 1 and 1/2. And it has this all-pass characteristic. It has a pole inside and a 0 outside, and they're at conjugate reciprocal locations. So if I was to put, let's put another one in here. And then 0.8 would show up in the middle here. See, it worked as expected. It's again perfectly all-pass. This is 1/2, that's 2. Or maybe it's not exactly 1/2 and 2, but these are conjugate reciprocals, and those are conjugate reciprocals. And if I go ahead and, in this example, I just prove that the magnitude response is constant, or down below here, I just picked a higher order design. And here I'm just using Python to make life easier. I'm saying define A to be 1, 0.2, 0.4, 0.3, and then use the third argument in the array indexing to say flip the order. This means count backwards, and the 2 colons just mean span, or the first colon means span over the entire array. Second colon behind it becomes the stepping function, which by default is 1, but if I set it equal to -1, it's going to step it backwards. So you can see B is indeed stepping backwards, and if I go with my z-plane here, this one is different. It's just got a complex conjugate pair, and if I go ahead and do the frequency response, and then here I did all 3 plots. 0 dB gain, there's the phase, and there's the group delay. But all-pass is guaranteed to have, unity gain if defined with that relationship, and some phase and some group delay. So now we're going to use that over here in the notes. It starts off with what could we do to move any of the zeros around, say from outside the unit circle to inside the unit circle. So what we would do is we would put a pole outside the unit circle and replace it with a 0 inside the unit circle, and that would be a transformation that would move a pole around, or move a 0 around using an all-pass factor. And the curious thing is any number of all-pass factors can be present in H of z. You can't see them from C of z because they are canceled out. The pole and the 0, the all-pass filter will, when you place it down, you'll place a 0 and a pole where the pole and the 0 are, so they'll cancel each other out. They're transparent in the C of z function, which kind of makes sense. It's like they're just there to map something. So this is an example kind of like what we just looked at. What are some properties of all-pass filters? Obviously, if you want to implement an all-pass filter, not just use it to cancel and add, the poles have to be inside the unit circle, but that doesn't preclude you from modeling a pole outside to cancel a 0 and then place a 0 on the inside. That's what we were just doing. So let me just go off to this. Suppose we have this system for h of z. I could implement an all-pass filter that would put a 0 here and a pole here, not in real time, but just in the mathematics of it. It can come along, and what it would do is the pen's not wanting to stay on. The poles outside the unit circle and the all-pass cancel, and you end up with zeros on the inside. Or you could do it the other way around if you wanted to. If you wanted to move a 0 inside to the outside, you could put the all-pass section in there. It just is doing an operation of moving things around to make it become minimum phase. So the first green circle there would be a maximum phase. This would be a minimum phase, because we already know we could just define it that way and it would have the same magnitude response. But the all-pass section could be a way of having it work behind the scenes to actually make that transformation, knowing that it has unity gain. It doesn't alter the gain to cascade with the all-pass. And in the end, you don't have any poles outside the unit circle. You just have a new system, which is the blue one down below. So don't be hung up by the fact that you have a pole outside the unit circle. Just in the mathematics part of the modeling, you do have just that as a sidestep. And at that, I just thought of something else I should show you. There is another document that I refer to. I'm trying to remember. It's in the homework, actually, right? In this hints page down below. Oh, I thought I put it in here. I'm visualizing it in my mind. It's not there. It's in the take-home exam. But I'm going to show it to you right now, and I'm going to put a link up for it too. It's down inside here. It's called Exam 2 Examples. So we're going to talk about this. I'm just going to give you a preview of it, and we'll come back to this more later. Suppose we start off with a system that looks like this. We can write this system as a cascade of a minimum phase and an all-pass system. So we have that 0 outside the unit circle. We write that, well, first of all, we write this as a minimum phase system. So we move the 0 inside, and then we cascade it with an all-pass, which we can implement because the pole's inside the unit circle to be causal, and then this will flip it outside. Take a more exotic example that has more poles and zeros in it. The minimum phase equivalent of this would take these 3 zeros and move them to the conjugate reciprocals inside. Leave the other poles as they are because they're minimum phase. They're making the system causal. So now we have a minimum phase system, and then we could cascade it with an all-pass to take it back to where we started from. So we have to take care of moving this 0 back outside the unit circle with the all-pass here and its conjugate here, and then we have the one on the real axis that we can move back. We're going to learn before today's over with that you could also do a minimum phase and a linear phase, but I haven't described the linear phase filters yet, but this does show up in some of the homework problems too, or at least these ideas do, the minimum phase, all pass, and other such things. Interesting, useful. This should teach you to become more astute about poles and zeros and how you can just be flexible. You can move things around if need be. So back over to here. This next section is just talking about some properties of all-pass systems. All-pass system, assuming that it's a causal all-pass system. So what I did in that little example of putting the pole outside the unit circle, that's just sort of a mathematical understanding about how it could happen. If you want to actually build and operate an all-pass filter that's causal and stable, then it has to have its pole inside the unit circle and its zeros outside the unit circle. But a fact of the matter is an all-pass system that is designed to be causal and stable will always have a group delay that's positive. So it increases the overall group delay of the system. And the phase is negative. And that's kind of a characteristic of any system that has delayed taps, and that it always makes the phase be negative. So the group delay is positive. The phase shift is negative as a result of adding it. And this is just a proof of that that's found in the book. So what people do in practical settings, if they want to compensate a system, you can take a system that has non-constant group delay and you can cascade it with all-pass filters to try to make the group delay finally be flat over the band of frequencies, just by putting in all-pass sections that will kind of level up the group delay in the pass band. And this is just the model of what the group delay works out analytically for each pole in the group delay. R would be the radius that the pole makes to the unit circle, and then theta is its angle. So now we're on to minimum phase systems and just discussing that further. A minimum phase system, like I've already said, is this definition here. All poles and zeros inside the unit circle. And if the minimum phase system has some zeros on the unit circle, it still is minimum phase. However, it has some relaxation in its properties, because it's not strictly minimum phase to put the zeros on the unit circle, but the properties, many of them still hold for a traditional minimum phase. And as I was showing you in the sketches from that web page, you can always factor any system as the cascade of a minimum phase and an all-pass. And likewise, a non-minimum phase system can always be made into a minimum phase system by just reflecting all of the zeros that are outside the unit circle to their conjugate reciprocals in the z-plane. The one caveat to doing that is you have to make sure, if you want to maintain the same DC gain, you also have to include gain scaling factors. So this is an example of what you would be going through, and actually the gain scaling example that we were looking at earlier, that I did in the notebook, or I haven't done in the notebook, but right over here. What I have circled in green, that's the gain scale factor that you need to incorporate. Just flipping the zero inside will change the DC gain, but then if you incorporate minus A conjugate, it'll make sure the gain is handled properly. And there's an example coming up here that does that. It's right here. Here's a stable causal system. You can see that the pole is at 1/3, and then there's two zeros, one at 3/2 angle pi over 4, and the other one at 3/2 angle minus pi over 4. So to make it minimum phase, we need to reflect the conjugate zeros inside the unit circle. But to do it mathematically, what we have to do is do some factoring on that. So we get set up by factoring it to look like the all-pass filter, a z to the minus 1, and then the minus 2/3 e to the minus j pi over 4. These are just the conjugate reciprocal locations, but then when you refactor this, it becomes what's up above here. But in the process of doing that, we're getting this factor that's the factor that comes out, and then there's two of them. One is the conjugate of the other, so the e to the j pi over 4 cancels with e to the minus j pi over 4, and you end up with 3/2 squared. So that factoring was done ahead of time. You can do it after if you want to too, but here's what it looks like following the factoring ahead of time. H of z, or H minimum of z, is now in there as the top square bracket, and then the all-pass filter follows that, and this all-pass filter is what takes the minimum phase zeros and moves them back to the maximum phase zeros in the picture to make your original H of z. So this 9/4 is the gain scale factor that is sort of hidden in the background. I say hidden because this will show up on the midterm too, so let me just say something about that as well. If I give you a pole zero plot, H of z, you're missing a piece of information, namely, if there's a gain constant in there, you cannot see that from just a pole and a zero. Is that right? You agree with me on that? To know that there's poles and zeros, you don't know if there might be a constant inside of there. So the way you can specify that constant you can say something like H. I might specify that H of e to the j 0 is equal to 1. I'm just going to make sure the DC gain is 1. So what does that mean inside of here? It would mean I would have something like k times double tapping my pencil does not work here. It works on my iPad. Okay, that would handle this case right here. We've got a pole P1, that's Z1, and that's Z2. I just didn't want to take the time to write it all out. But from the picture, you can write out the mathematical form of the ratio of the polynomials, Z1 times Z to the minus 1, and so on. And then you can put in an unknown constant K out in front, and then you can figure out what K needs to be based upon what this is. So you would set Z to the minus 1 equal to 1, and then backwards solve for K. So you can always handle that case if you have to. Some of that goes on in homework set number 6. It also goes on in the take-home exam, where I specifically say, remember to incorporate the constant, because I say, look, I've already said it has to be unity, say at DC, which says that you have to hypothesize there is a K in there somewhere.
Did you say to set the z to 1 because e to the j 0 is 1?
Yeah, exactly, yeah. I could take time to do that. I'm just really watching the clock. We can come back and drill into this some more. Here, though, it was handled by doing this factoring ahead of time to make it be minimum phase. So this is H all pass, and then H minimum is there, and then in order to go from the maximum phase to the minimum phase from the original H of Z, and 9/4 had to come out of that with the factoring. So that's ensuring that the gain is a constant. Because I'm kind of dashing for time right now, I'm going to go back over to the notebook, and let's see, close the wrong window. I'm going to go back over to this simple example that we worked. Where I wanted to reflect that 0 to the inside. So if I need to reflect that 0 to the inside, what I really have to do is I have to put a factor on here, and see, how can I make this look the easiest? I'm just going to try to rewrite this. I'm going to use this because it's a smaller example than what I have, any of the examples I have in the notes right now. So now I'm going to, let's see. H min and H all pass. Let's see, how do I want to do this where I'm not going to be too confused by the whole thing? See, by doing this factoring, I get this minus 1/2 that comes out in front. And then if I just look at these two things, this is the all pass that I'm looking for, because it's going to cancel the pole. It's going to cancel the 0 at 2 with a pole over here at 2, and then it's going to put in the 0 at 1/2. So the factor that I need to incorporate now is going to be that minus 1/2. So if I go back to this problem over here, this was my system that I started with, and when I inverted it, what I did was I just simply put in the minus 1/2 for the 0 in the numerator, or the pole in the denominator. So what was I missing? I was missing the minus 1/2, so there should be a minus 1/2 over here. So I'm going to convert this to an array. Otherwise it's a list, but now I can multiply times minus 1/2. And I'm going to change this from group delay back to gain. Notice now that it is at 0 dB. I didn't have that before because I had nothing in there. I had 1. So it ended up with a positive gain, but I didn't do the factoring. I didn't make it B unity gain. In the exam problem, I don't care whether you incorporate the gain or not because it still works, and I described that. But if we were doing an exact representation of the channel, we would want to do something like this. So we'd end up with minus 1/2. And now you can see that the gains cancel back to 0 in spite of the fact that the phase is not 0 in the system because we've done a minimum phase equivalent. We have, well, the group delay was probably better in this case, remember? Did that. The green is H times H inverse, and it's the smallest amount of group delay variation of both systems. So the equalizer is definitely doing something, right? Flattening the gain perfectly and trying to minimize the group delay variations, not perfectly. There has to be a compromise though, or has to be something when you go to the minimum phase equivalent. You lose something, but you still get quite a bit. And you'll get a chance to see that in action in this exam problem by characterizing it in a different way than this. It'll be characterized in the time domain. I think I'm still going to come across another problem in here, so I'll just press on and see where I get to. But that's what was done here. That's what the 9/4, where that came from. Here we weren't doing an inverse. We were just trying to get the minimum phase written out, and in terms of writing out the minimum phase, there had to be this factor incorporated in there. Here is a return back to the inverse idea that I said would come back again, frequency response compensation for a channel. So the distorted system is minimum phase, then we can just invert the distorting system perfectly, not a problem. But if H of D is non-minimum phase, and that was what we were just looking at in Jupiter, and this is what you have in the exam problem, then we have to incorporate an all-pass filter to form a minimum phase system. And here's the block diagram. The distorting system is this. You compensate it to make it minimum phase, and then you can actually build the compensating system, which I guess I call G of Z is, let's see, 1 over H minimum is HC. Yeah, that's what you're doing, you're compensating it. So this is the this is the idea of what you do in the exam problem. But I did it in Jupiter, and the Jupiter example I think is clearer because it's more hands-on. You can just use that as a starting point and just visualize what you have to do. I do an example. This is based on an example in the book of compensating a 4th order system. So if you see this is your distorting system, what should jump off the page if you want to build an inverse for this system? What you need to do first? You look at that and what should hit you immediately. The zeros that are outside the unit circle have to be flipped inside. The exam problem, I ask you to make this plot right away so you can just, it'll pop off the page and hit you. What do I have to do? I don't have to touch the zeros inside. I just need to manipulate those guys that are outside. Does that make sense? So then I proceed to do that. I don't show the math here. I'm just showing the results. So the non-minimum phase system in the end, these are all, this is group delay. Trying to think, what do I have? Yeah, When I get all the way done with this, I end up with a group delay that is, I think, this guy, and the gain is exactly unity. So this is just a more exotic version of what I was doing in Jupyter. You can look at this, but what I did in Jupyter, I forgot I had this example. So when I was working this up yesterday and I had reworked the exam yet again, I said I'm going to put something in a Jupyter notebook that'll help you get started with it. That's a little bit more practical. This is good, just the same. In the end, though, it perfectly compensates the gain. It doesn't perfectly drive the cascade group delay back to the constant value, but it does do something good. Okay, properties of minimum phase systems. Minimum phase system has the minimum amount of phase lag. I'm not going to prove it, I'm just stating it here. So they're additive, and remember, all past systems always have a phase that is negative. So if you go through the sum and then do the derivative to go from phase to group delay, it says that because we have the minimum amount of phase deviation with the minimum phase system, it has the smallest amount of group delay. Then there's the minimum group delay property. I'm going to skip over that one. Third property is minimum energy delay. There's a bonus problem on set number 6, and it swirls around this minimum energy delay property. If the minimum phase system has the same magnitude as the system, and it does because all past systems are relate the two, then the question is how do the impulse responses change between the system and its minimum phase equivalent? What this property says is that as we add up the impulse responses energies, which is the magnitude squared of the impulse response terms, in a cumulative fashion to form E event. In other words, we start at 0 and then just keep working our way further out in the impulse response. The minimum phase system will always most rapidly climb in energy because it's on the right-hand side here. It's always greater than or equal to what the original system has. And there's a sketch of a proof from the book, but here, this is very similar to the homework problem. You're given a pole zero plot for this system, and these are all the different permutations. This is minimum phase. This is going to be what? Maximum phase, because they're all outside. And then these are the mixed phase, 2 inside, 2 out, 2 outside, 2 in. So if you accumulate the energies, or look at the impulse responses, and then draw the energy plot, cumulatively summing the magnitude squared of the impulse response terms, it's the minimum phase one that starts out ahead and finishes ahead. So the energy is packed into a smaller time window than it is for the non-minimum phase, which intuitively also makes sense. Information gets sent with the least amount of effective delay because it compresses the sending of the information over the earlier taps of the channel. In the idea of a radio channel, it's having taps spread over a time interval is what we call multipath. So that's a bad thing. If we disperse the energy in a radio channel on the ground between soldiers or whatever, we're making our channel be less effective because we're putting in dispersion, which means we can't send out as high a bit rate without smearing the bits out. So the equalizer tries to resolve that as best as it can. But the radio channel is what it is. We can't change the radio channel because we have person A and person B, terrain, and so on. You just have to work with it somehow or another. Strangely enough, though, it might be that you transmit up in space, come down in space, take the terrain out of the equation because each person can see space, then they don't have a channel problem, but they do have a propagation delay, just the time delay in going up and coming down is present there. Okay, last topic, linear systems with generalized linear phase. So this takes us back to quite a while ago. Suppose we have a desired system, h of e to the j omega. It has a pretty wild magnitude or phase response, but suppose it's anything we want, we can put in the first box in the block diagram. We can just get our favorite magnitude response, put it in there, and then linear phase system will at most allow it to be cascaded with an e to the minus j omega alpha, so that would be linear phase. This is just a fictional idea. It's like, what if you're dreaming, if I could just get any magnitude response I like, say within the Paley-Wiener theorem that we talked about, so it can still be causal, but we just want to throw away the cruddy phase response and put in a pure delay of alpha samples. So we saw a while back that a ideal brick wall filter can be approximated by taking a sync impulse response, and then we can just delay that and we can kind of get what we want, but we can't build that filter. But that's just to give you an idea of how you could get something that has pure linear phase. Generalized linear phase turns out to be a relaxing of the condition. It says we just want, guess what, my ear just got plugged up down here, so now all of a sudden somebody turned the volume up in my right ear and it's blowing my head out. I'll try drinking some water and see if it'll go down. I guess I can't talk for 3 hours anymore without having this problem, is what's going on. You have a real function a, which could have sign changes in it, a, and then you can have a linear phase term, the alpha, and then also a 90-degree phase shift, beta. So that's the definition of generalized linear phase. It's loud. I wish I could. I guess when I sat down, yeah, when I put my head down, it goes away, and then it comes back again. I stay too busy, so I haven't had a chance to make an appointment with my doctor about anything. I haven't had a physical for over a year, so I'm in a bad way, if you think about it. So you can work through the real and imaginary parts and write out, and this is just a bunch of math, but this just comes down to say I could build a linear phase system if I could figure out how to choose H, alpha, and beta to sum up to 0. So that's a necessary condition. It's not a sufficient condition for ensuring linear phase. And it certainly is not a design equation. It's like, what do I do with that? You can't play around with that. So we also want the system to be causal. So then this is what the condition becomes. So this is our necessary condition, but to actually make it work from a design standpoint, we end up just coming up with a known solution, which I'm sorry to say I don't have a proof of it. I'm just going to show you that it works, though. And this is the case of even and odd symmetric coefficients suffices here. So we just need to make our coefficients in an FIR filter be either even or odd symmetric, and we've got a generalized linear phase system. So here's those two cases sort of written out. When you go with odd symmetric, beta can be pi over 2 or 3 pi over 2. When you go with the even symmetric condition, then beta can be 0 or pi. And of course, alpha is related to the number of terms in the even symmetric system. It's really good to put my head down. It's very not so blastingly loud. So there's 4 types. There's a type 1, type 2, type 3, and type 4. And they have to do with whether it's even or odd and whether M is even or odd. So there's 2 even and odd components to this. But type 1 is even symmetric and M is even. So you can go through the math for the frequency response, which I just have written out in all its gory detail. And finally, when you put it all together, it comes down comes down to this right here. Comes down to that if the AKs are chosen to be related to the H's through this representation, and this is just the symmetry, it's saying terms outside of the center term are all symmetrical as you work your way out, and the center term gets to choose all by itself what it can be, then this is what the frequency response becomes. There's a linear phase, m over 2, and that's a delay of m over 2 in terms of the filter order, and then there's this function of frequency that's left over. So that's type 1. Type 2 makes the order odd. So now the number of taps is even. The order is odd. Remember, a polynomial of second degree has 3 coefficients. So if m is odd, then we have so many terms on either side. There is no central term. So we have just terms on either side, and that's the B terms in this model. But this is the same idea, though. If we go with odd symmetry, then we can have m even and m odd. If we have the odd symmetry, and then you map the coefficients to be CKs from the H's. I'm going fast because I'm looking at the clock. And then the 4th case is odd symmetry, and M is assumed odd. Why am I going so fast? Is because this picture, I like pictures. This picture kind of sums it up. Type 1, you have an odd order polynomial. So you have an even order polynomial, but you have an odd number of taps. So you always have a central tap. That's the point of symmetry shown here, and then everything is symmetrical about that center tap, which can be anything. Type 2, the polynomial order is odd, so the number of taps is even, so you have half the taps above, half the taps below. The point of symmetry is going to be an odd half integer, so there's no tap there. Type 3 has got odd symmetry and an even order polynomial, and in order to make odd symmetry hold, you cannot make that center value be both positive and negative, so you're forced to make it 0 in this type 3. And then in type 4, the center is an odd half integer, so you don't have to worry about that. So those are the way the taps break down. The really cool thing that comes out of this is conditions, and I'm going to have to summarize that due to the time. The conditions on where the zeros get placed in a linear phase filter. So the zeros get placed in several different standard forms, and that's the conditions talked about here. The symmetry conditions impart how the zeros can be located to make it linear phase. They reflect, in a sense, if you have an even symmetry filter where the zeros are going to be, and that's a pretty cool thing, and I have that summarized in a table too. So it's right here. If you have a type 1, the zeros just have to occur as reciprocals along the real axis, and then they have to occur as conjugate reciprocals on the unit circle, and if they're not on the unit circle, then they have to occur in quadruplets. So if you want to put down a 0 here to maintain real coefficients, you have to have 1 here, but then the conjugate reciprocal property says you have to have 2 more. So this is like multiples in pregnancy. Since my wife bore twins, I think of it that way. If you want to put a 0 off the real axis and you want it to be conjugate, so that you can do cool bandpass things with it, you have to put down 4. So you have to have quadruplets. That's the only option you have to maintain linear phase. If you want to have them on the real axis but not on the unit circle, then they have to occur as a pair or twins, and they can individually occur off the real axis on the unit circle as a pair. Once again, that's just for conjugate symmetry reasons. When you go to a type 2, you're forced to have a 0 there. When you go to a type 3, you're forced to have 2 zeros. And when you go to a type 4, you're forced to have a 0 there. These are just how the roots factor out when you have these different symmetry conditions. How does that grab you? I mean, it says something, right? This would be okay for building a low-pass filter because we can't pass the high end with a 0 plop down there. This would be okay for not a low pass or a high pass because there's 0 forced both there and there, but this one would be good for high pass. In general, these last 2 types are good for building Hilbert transforming filters because you also have 90-degree phase shift through these filters. So I have I'll say a plethora of examples that kind of bear out these properties. I also have these in the Jupyter notebook over here too. Let's see. So I just picked some polynomials for the numerator FIR that were symmetrical. And there it is. So this is odd order. So guess what? It's got a 0 right there. It has to have that. This is even order 6. So there's 1 quadruplet in there, and then there's 1 twin because of the lying on the unit circle. But there's nothing there. And then here, I did an odd symmetry case. This is odd order, so it only has to have a 0 out there. And then down here, I designed, using filter design tools and FIR design helper, a 53rd order Ramez filter. All these zeros form the stop band, and then all these quadruplets are forming the pass band. Notice how they obey the properties, though. This is a linear phase because I see the quadruplets, I see the pairs on the real axis, and then I see the pairs on the unit circle. And if I go ahead and look at the magnitude response, it's nice equal ripple. If I look at the group delay, I guess I didn't do a plot of group delay. I can do a plot of group delay, though. And I got to take that out of here. Group delay is a constant. It's at half the filter length. So this is 52 or 53. So 52 divided by 2 is going to be 27. Is that right? So that's the group delay of the filter. Exactly the midpoint of the filter is at 27 taps. There's the impulse response. So I can see that that center tap there is indeed the group delay. 27, 28, 29. I guess it's at 28. Didn't do my math right. What am I missing? This is all rolled up into the homework for sure, and it will be things chosen for the midterm as well. We're out of time though, so we've got to get out of here. I'm going to go up to the lab. I'm going to take Kaylee's question, and if anybody else that's not in the lab wants to come and talk to me, you can do that.